Yeah, so this is the lecture number 33 on centrifugal pumps again. So, mostly as I said in the previous lecture, so we will be focusing more on pump power requirement estimation. So, here there is a total pumping head is the total energy utilized by a pump in order to pump from low head to high head. Okay, so here there are two situations you can see based on the location of the water source. So, if the water source is above the center line of the pump, right, and the water source is below the center line of the pump. So, water source is above the center line of the pump. For example, here if you see, so this is the center line of the pump. Okay. So, the water source is above, and in this case this is center line of the pump and the water source is below. In both cases we are going to see what is the total head. So, our idea is if you remember the equation, the power which is equal to Q into H divided by 76. So, this will, so H is the head. So, here in both cases we are going to see what is the head. In this case what is the head, and what is in this case what is the head. Okay. So, and the discharge anyway will be knowing. So, knowing the discharge, right, and the problem is the head. So, head involves the real pipelines and then friction head losses, okay, then other head losses. So, we are going to the main task is to find out what is the total head here in both cases. So, let us see the case number 1. So, that is the water source is below the center line of the pump. Here if you see the center line of the pump below, and it has a static suction lift. So, since this is the pump center line, it is below. So, we use the term lift. Okay. If it is above, we use the term head. Okay. So, in this case the static suction lift. Okay. So, the vertical, this is the vertical distance between from the free surface of water level to the center line of the pump. This we already in the previous lectures we have defined this. So, this is, if you see the static suction lift. So, this is from center line to the water surface. So, that is static suction lift, and then total suction lift. So, that will be suction static suction lift and then the friction head losses in that pipe. Okay. So, this is a total suction lift and static discharge head. So, this is the suction is done. So, we have the two parts here. One is a suction part and then a discharge part. So, in both cases we are going to estimate the head losses individually. So, as I said, so here, so this is the suction case, we have two parts. One is the suction lift and the friction head losses which are present in the suction pipe. So, and also in addition to that we have to consider the bends, okay, which are present in that, and also the velocity head. Okay. So, and then the so here if you see theoretically, so from moving one place to another place, the water in a pipe. So, there is a elevation head, right, plus pressure head plus velocity head, okay, from velocity head. So, so the elevation head, of course, that is due to the pipes, the height and everything. The pressure heads, that is due to the frictions and other things, and the velocity head. So, these three heads we need to consider here. So, total suction lift will be suction lift plus and total static suction lift plus friction head, and then static discharge head. Similarly, the static discharge head will be your the discharge head, static discharge head plus the static discharge head. See, this is the vertical distance. So, static discharge head is, this is the pipe center line to the top surface of the delivery. So, this is the static discharge head. Okay. And then you are going to have the friction head loss in that, and that will give the total discharge head. So, that is HSD and HFD. So, velocity head, that is V square by 2 z you need to consider, and the total head will be the suction, right, discharge and velocity. So, this is the total suction head, total suction lift, total discharge head and the velocity head in both the suction as well as discharge case V square by 2. So, this is the total head in case of water source which is below the center line of the pump. Similarly, the water source which is above the center line of the pump, if you see. So, in this case also we consider the suction case and the discharge case, both cases. Okay. So, in this case the static suction head, because this is above center line. So, static suction head. So, that is the vertical distance between the top of the surface and the center line of the pump, and then total suction head. So, that will be Hs minus Hfs. So, Hs minus Hfs, this is friction head loss, but the negative, because this is we are not going to use any energy to pump, because it is a gravity, due to gravity anyway. So, gravity is helping us. So, it is a negative basically, the head is negative here, right. So, that is why it is a negative head, but the difference of suction head minus friction head. So, then static discharge head. So, that is same as before, because we are not changing anything here. So, this will be same. So, one is the difference between static discharge is the difference between these two. This is the discharge head and then adding the friction head loss here. Okay. So, then the total discharge is the discharge head, static discharge head and the friction head loss, and you have to use the velocity head. So, the total head in case of so water source above the center line of the pump is equal to, this is the static suction head, static discharge head, total discharge head, total suction head, and then suction, this is minus V square by 2 z, and V square this is for discharge, velocity head for discharge, V square d by the 2 z, because here the velocity, if you see again, this is coming down, this is really helping. So, that gravity really helping us in pumping. So, the pump does not require to use extra energy to pull this water, because it is anyway head. Okay. So, that is the reason velocity is negative here, and with this in both cases we found the total head. So, once you know the total head, once you know the total head and the discharge, total head and discharge divided by 76, you get, this is the water horsepower. So, water horsepower, that means in order to pump water from one place to another place, this much HP is required, and then so that is the water. Then after that, in order, this is the pump level, right, the pump level. So, this is the pump, suppose this is the water, right, and here there is a motor which really operates this pump, right, operates this pump. So, there is a shaft, right. So, shaft is connected between the pump and the motor. So, here this has, so because this is in a moving parts, both those are moving parts. So, at this point, this is called shaft horsepower, which is equal to water horsepower divided by pump efficiency. So, how efficient is the pump? So, that will be shaft horsepower, and then the next is the brake horsepower, which is equal to shaft horsepower divided by efficiency of the drive. Okay. So, that let us see that. Next, if you see, yeah. So, in case of monoblock pump, so BHP is equal to SHP. So, brake horsepower is actual HP supplied by engine or drive to a pump. Okay. So, in case of BHP, monoblock, brake horsepower is equal to shaft horsepower. In case of belt drive, so we have to put the drive efficiency here, WHP by drive efficiency, you get BHP here. Okay. And then input horsepower. So, this where the electrical energy, I mean there the motor really works, water horsepower divided by I. So, generally IHP, which is equal to BHP divided by efficiency of the motor. Okay. Since BHP is water horsepower divided by drive efficiency, and then pump efficiency, and then motor efficiency. So, that is what you get this equation from this equation. So, BHP here is equal to WHP divided by pump efficiency and drive efficiency. Okay, so, NP pump efficiency, motor efficiency, and the kilowatt electrical motor, that is BHP into 0.746 into motor efficiency. So, this equation will be used to find out the electrical motor, I mean power required to run the motor. Okay, so this overall view this will give. So, here we have water. So, water Q indication 76 will give the water horsepower. So, since the pump has an efficiency here, engine has an efficiency here, drive has an efficiency here. So, at this point shaft horsepower, so that will be equal to WHP divided by NP. So, divided by NP. So, shaft horsepower, and then the BHP. So, that will be is equal to SHP in case of monoblock, otherwise BHP is equal to water horsepower divided by ND, right, so ND into NP, okay, or BHP is equal to SHP divided by ND, okay, in case of this. So, then putting engine efficiency also, motor efficiency, you get I mean IHP is equal to BHP divided by NM. So, that will give the engine efficiency. So, everything is here. So, how to find out the motor efficiency? So, here from if you see the pump testing rig, basically the electrical energy which is supplied as voltage into current, that is P in, and power out will be estimated using a torque and angular velocity. So, that is T into RPM into 2 pi into 60. So, there is a torque meter is there, and RPM is estimated, I mean measured. So, knowing this, T into double P out will be known, P out by P in is equal to motor efficiency. So, this way you can see how efficient is that. So, exercise here in this problem. In this problem, a pump lifts 100,000 liters of water per hour, operate at a total head of 20 meter, and compute the WHP, water horsepower. So, if the pump has efficiency 75%, what is the size of prime mover required to operate the pump? So, if a direct driven electrical motor with an efficiency 80% is usual to operate the pump, compute the cost of electrical energy, a unit of 30 days. The pump is operated for 12 hours daily, 30 days. So, the cost of electrical energy is 6 rupees per unit. So, we know W horsepower, water horsepower, which is equal to discharge into head by 76, you get 7.3, and shaft horsepower, W horsepower by pump efficiency, you get SHP. Since the pump is direct driven monoblock, so this will be BHP. So, knowing the BHP, we can find out IHP, right. So, here if you see, so this is BHP multiplied by 0.746 into motor efficiency. So, you get the kilowatts. right. So, total energy consumption is the kilowatts into 12 hours a day and 30 days. The total these many kilowatt units, and cost of electrical energy is kilowatt watt hours and 1 unit cost. So, 1 unit is 1 kilowatt hour. So, total 19,590 rupees is the electrical energy cost in rupees. And this is a big example, of course. It has a direct driven centrifugal pump coupled with 3-phase electrical motor is installed in a deep well. The discharge rate of pump is 20 LPS. The pump efficiency is 70%. The center line of the pump is 60 centimeter vertically above the static water level and 6 meter above the pumping water level. Okay. So, that means this is the first case of this is the pump, and you have the water source just below the pump center line. Then the suction pipe is 7.5 meter. So, this is suction pipe 7.5 meter long and 8 centimeter diameter. A foot valve is with strainer is attached to the bottom of the suction pipe. The suction line is connected to the pump inlet by long sweep bend, same size of suction pipe. The pump discharges water into the top of the pump stand in an underground pipeline water distribution system. The vertical distance between the top of the stand and the center line of the pump is 20 meter. The total length of the 7 centimeter diameter discharge is 20 meter. The pipe fittings on the discharge side are 3 long sweep bends and 1 gate valve and 1 reflux valve. All of them are the same size at the discharge pipe. Okay. So, find out the total head, water horsepower WHP and brake horsepower, right, the BHP. So, these things needs to be worked out. So, let us see here. So, the whole thing can be put in this manner. So, this is the pump. So, this is the suction line, and at the end there is a foot valve. Okay. So, here this is sweep bend, there is a sweep bend, this is a gate valve, a reflux valve, there is another sweep bend here, and this is the delivery. The pump has 70% efficiency. Okay. So, this way, if you can schematic the whole thing, then the calculations are like this. So, first area of suction pipe, since the diameter is given, so you can find out area of suction pipe and velocity of suction pipe. So, knowing the discharge and velocity as discharge and area, you can find out the velocity. Similarly, for discharge pipe area and velocity. So, and the first thing is the total head. The total head is equal to total suction lift and total discharge head. Okay, this is the total head. So, we find out total suction lift and find out total discharge head. So, once you know the total head, and you will be able to find out the water horsepower, which is equal to Q into H by 76. So, our interest, so Q is known, our interest is to find out H, so total head. So, the total head as I said, the two parts, suction lift and discharge. So, let us find out what is suction lift. So, it has again static suction lift and friction heads, velocity heads. Okay. So, static suction lift 6 meter suction pipeline is given. So, 6 meter head loss in the suction pipe 8 centimeter dia 7.5 meter length is 2.25. So, from friction loss table, so there is a table I said, right. So, this is the Q for a particular Q, and these are the diameter for a particular diameter. You get the friction head loss for 100 meter length of the pipe. Okay. So, for 100 meter length you got HF, and for this length 6 meter length, right. So, what would be your HF? Suppose this is 100 meter, you get HF, and for 6 meter what is this? Okay. So, that is 6 by 100 into HF. Okay. So, that will be 2.25 if you look at that, and head loss in the long sweep bend 8 centimeter diameter, that is 0.41. So, this is also similar to, so you have seen the you know, the for different bands, you have seen for a particular discharge, right, you get an equivalent length of the pipe, right, equivalent length of the pipe. and you go back to your friction table for 100 meter, find out HF, and for L find out the HF. Okay. So, that is 0.41. Similarly, for head loss in the strainer, so there is an equation K S into V square by 2 Z. So, velocity is given, I mean estimated, we have estimated a velocity, and then you get 0.77 meters for the strainer. So, strainer, why for the suction we have the strainer and footwall. So, similarly, okay, so here there is a friction head loss table. So, knowing the discharge here and the corresponding diameter, you can find out the friction head loss for 100 meter length, and then you can reduce it to your length. Okay. Yeah. So, similarly for walls, for long sweep bend for example. So, for a pipe size, find out this is equivalent pipe length, and then go back to the friction table and find out the corresponding HF for this particular length. Okay. So, now head loss in the footwall, this is this much, use the equation, velocity head V square by 2 Z, you get this, and total suction lift is a static suction lift. Okay. And then you get the friction head loss in the pipe, and this is the bend, this is the strainer and the foot valve, okay, velocity head, and then other bends. So, the total will be 10.89 meter is the total static suction lift, okay, total suction lift, this one. Similarly, static discharge head 20 meter, this is the length of the pipe, and then head loss in pipe for 7 centimeter 20 meter length, you get 14.4 meter is the friction head loss, and the head loss in the long sweep bends. So, 7 centimeter you get 2.07 meter, right. Head loss in the gate valve 0.33 meter from the, again this is from the table. So, this is from the table, this is also from the table, a nomograph, this is also from the table, right. Head loss in the reflex valve based on the foot valve, if you use the same foot valve equation like Kf into V square by 2 Z, you get this, and velocity head discharge line, that is again V square by 2 Z. So, that is 1.40, right. So, in case of discharge head, the total will be, this is the discharge line, length of discharge line, and 14.40 is the friction in that line, and 2.07 is the what you call the bends, and then this is what reflex valve and other bends. Okay. So, all together it will be 39.32. So, total head will be, this is the suction side and discharge side, and total will be 50.21 meter, and water horsepower is equal to this is the head and discharge divided by 76, will be 13.21 HP, and brake horsepower of motor required will be 13.21 divided by 70 into 100, that will be 18.87 HP is the brake horsepower. Okay. So, this way in the centrifugal pump, so we covered in this lecture, if you install the centrifugal pump in two cases, the case number 1 when the water source is below the center line of the pump, I mean you estimate the total head loss, right. So, basically the head loss will have two parts. The part number 1 is the suction lift, right. So, in this case it is the suction lift and also discharge head. Okay. So, in case of water source which is above the center line of the pump, the suction head and the discharge head. Okay. So, these two heads we need to consider for finding out the total head. So, in each part either suction or discharge, so if you can I mean divide. So, it has the basically the elevation head, the pressure head and the friction head. So, these three heads pressure head, friction head, velocity head. So, these heads will be considered. Okay. The first thing is the pipe line, the length of the pipe, so that will give the elevation head. Okay. And then the friction head loss is due to the pipe length. So, that will be the friction head loss, and then the velocity. So, velocity due to the turbulence and other things. So, that will create velocity head. Okay. So, these three heads, then in addition to that, if you have bends, you have to consider the friction head loss due to bends. Okay. So, similarly in case of discharge side, so combining all heads together will give the total head. So, knowing the total head, right, multiplying with the discharge divided by 76 will give the water horsepower. So, that means the water to displace from suction to discharge head, discharge level, you need to operate the pump at this particular HP, right, power. So, then again the power will be different from end of the pump, like starting of the pump to the motor level, electrical motor level, based on the efficiency of the devices. Okay. And based on that, it has been like you have water horsepower at the starting of the pump, and then shaft horsepower combining the pump efficiency, then brake horsepower. So, that will be like, you know, if you have monoblock pump, so the shaft horsepower is equal to brake horsepower, and then if you have external drive is used to operate the pump, then you have to consider the drive efficiency into calculation. So, then your brake horsepower is equal to shaft horsepower divided by your efficiency of the drive, and then input horsepower. So, that is equal to, so input horsepower is equal to brake horsepower divided by efficiency of the motor. Okay. So, at the different stages the efficiencies are different, so that the power is the different, HPs are different. Okay. So, we solved the two examples here. The first example on the power requirement, the second example also on different cases. I mean, finding out, knowing the total head. So, how to find out the total head for a particular case. So, case number 1, in this case, like water source is above the center line. Similarly, you can find out the case number 2, the water source which is above the center line, this case number 2, the total head. Okay. So, in the next class we will be focusing on what is the cavitation in a centrifugal pump. Generally it happens, and then pump characteristic curves, affinity loss, and then there are other pumps we need to discuss. Okay. Thank you so much.